Um, Structuralism in the Philosophy of Mathematics. First published Monday, November 18th, 2019. Substantive revision. Wednesday, September 17th, 2025. The core idea of structuralism concerning mathematics is that modern mathematical theories, always or in most cases, characterize abstract structures instead of referring to more traditional kinds of objects. Hold on. Sorry. Okay. Um, uh, is that most modern mathematical theories always, or in most cases, characterize abstract structures instead of referring to more traditional kind of objects, including sets, or of providing mere calculating techniques for application. Thus, arithmetic characterizes the natural number structure analysis. What the fuck? Thus, arithmetic characterizes the natural number structure, analyzes the real number structure. In traditional geometry, the structure of Euclidean space. As such, structuralism is a position about the subject matter and content of mathematics. But it also includes, or is closely connected with, views about its methodology, since studying such structures involves distinct tools and strategies. Hence, there are two related kinds of structuralism: metaphysical and methodological. In English language philosophy of mathematics, the introduction of structuralist views is often taken to have happened in the 1960s in works by Paul Benacerraf, and Hilary Putnam. Our survey will start there as well. Debates about structuralist views picked up steam in the 1980s and 1990s when Michael Resnick, Stuart Shapiro, Jeffrey Hellman, Charles Chehara, and Charles Parsons entered the fray, and they have been reshaped again during the last 25 years through philosophical challenges to and novel variants of structuralism. Most of those challenges and variants involve metaphysical issues, especially questions concerning how to think about mathematical objects and about mathematical truth along structuralist lines. But a few also concern epistemological questions. However, mathematical structuralism played a role already before the 1960s, especially if it is understood in the methodological sense, where questions about how to organize, articulate, and innovate mathematical practice are at stake. Structuralist positions in that sense go back to the 19th and early 20th centuries, in writings by Dedekind, Klein, Hilbert, Poincare, Noether, Bourbaki, etc. Today, the two most influential versions of methodological structuralism are set theoretic and category theoretic structuralism, both of which lead back to metaphysical issues, mainly by being related to foundational ones. Relevant debates will be covered in the later parts of the survey. It will end with some brief remarks about structuralism beyond mathematics. Holy moly. Okay. Maybe we can, we'll see. Section 1, or we'll just go down the ladder. Section 1. Eliminative versus non-eliminative structuralism. Section 1.1. Beginnings of the structuralism debate in the 1960s. The discussion of structuralism as a major position in English-speaking philosophy of mathematics is usually taken to have started in the 1960s. A central article in this connection was Paul Benacerraf's What Numbers Could Not Be. The background and foil for this article was the position, dominant at the time, that axiomatic set theory provides the foundation for modern mathematics, including identifying all mathematical objects with sets. For example, The natural numbers, 0, 1, 2, etc., can be identified with the finite von Neumann ordinals, starting with /0 or for 0, and using the successor function f, x translations into x slope parentheses x parentheses or something. Okay. Neumann ordinals. What the fuck is this supposed to mean? Let's see. Show what? Show math as math ML code? Oh god. Wait, I don't know what I'm doing or looking at. I guess that's kind of cool. Okay. Show me as like code. Okay, whatever. Similarly, the real numbers can be identified with Dedekind. I'm guessing that's what that refers to. Okay, it's a guy, Richard Dedekind. Be identified with Dedekind cuts, constructed out of the set of rational numbers. Arithmetic truths are then truths about these set theoretic objects, and this generalizes to other mathematical theories, whose objects can be identified with sets as well. As Benacerraf argued in his article, such a set theoretic foundational position misrepresents the structuralist character of arithmetic in particular and of mathematics more generally. Thus, instead of working with the finite von Neumann ordinals, we can work equally well with the finite Zermelo ordinals, starting again with 0, 4, 0, but using the alternative successor function. And infinitely many other choices are possible too. Similarly, instead of identifying the real numbers with Dedekind cuts, we can work with equivalence classes of Cauchy sequences. Again, constructed set theoretically out of the rational numbers. I don't understand anything I'm fucking reading right now, as suggested by Cantor and others. This insight about a multiplicity of options is hard to deny, and even set theorists, foundationalists, can agree with it. For more on set theoretic responses to this challenge below. But Benacerraf drew further and more controversial conclusions from his basic point. Benacerraf suggested, in particular, that the natural numbers should not be identified with any set theoretic objects. In fact, they should not be taken to be objects at all. Instead, numbers should be treated as positions in structures, in contrast to the set theoretic representatives mentioned above. All that matters about such positions are their structural properties, i.e., those stemming from the relations they bear to one another in virtue of being arranged in a progression. What we talk about in modern mathematics, then, are the corresponding abstract structures. Example, the natural number structure and the real number structure. It is in this sense that Benacerraf suggests a structuralist position. The further details of that position are left open, however, including how to think about abstract structures, except they are not to be identified with set theoretic relational systems, i.e., models of standard model theory. Second article from the 1960s that was influential in the rise of structuralism is Hilary Putnam's Mathematics Without Foundations. As in Benacerraf's case, for Putnam, the FOIL was a set theoretic foundational position, where all mathematical objects are identified with sets. This position is sometimes, although not always, understood in a realist sense, most famously in Gödel's 1964, i.e., as the description of an independent realm of abstract objects, namely the universe of set sets characterized by the Zermelo-Fraenkel axioms. In opposition to such set theoretic realism, Putnam suggested a form of if-thenism, a suggestion that can be traced back to the discussion of non-Euclidean geometry in Russell 1903. This alternative can again be illustrated in terms of arithmetic, now taken to be based on the Dedekind piano axioms. How should an arithmetic theorem, say 2 plus 3 equal 5, be understood now? Should be analyzed as having the following form. For all relational systems M, if M is a model of the Dedekind piano axioms, then 2m plus 3m equals 5m. Here, 2m, 3m, and 5m are those objects that play the roles of 2, 3, and 5 in the model M. Similarly, for the real numbers, based on the axioms for a real closed field originally formulated by Dedekind and Hilbert, instead of if-thenism, one can characterize Putnam's position also as kind of a universalist structuralism, since it involves universal quantification over relevant systems, and those systems are kinds of structures. Often, an objection to such a position is the non-vacuity problem. Non-vacuity? Or should I just vacuity? Lack of thought or intelligence and vacuity. Yes. Such position is the non-vacuity problem. It is based on the observation that if-then statements of the given form are vacuously true if there is nothing that satisfies the antecedent, right? Precedent and then antecedent thing or event that existed before logically preceded. Antecedent if then statements of the given form are vacuously true if there is nothing that satisfies the antecedent. Example, if there is no model of the Dedekind piano axioms, a sentence like 2 plus 3 equals 6 would then also be true. In response, axiomatic set theory can be invoked as providing the needed models. But from Putnam's point of view, this is unsatisfactory for two reasons. It relies on a foundational view about set theory, thus undermining the anti-realist thrust of if-thenism, and set theory is then treated differently from other mathematical theories on pain of circularity. As a way out, Putnam suggested working with modal logic instead, but the exact details were again left open. Section 1.2, Consolidation and Further Discussions in the 1980s. One way to understand Benacerraf's 1965 article is that it proposes to treat the natural number structure as a new kind of abstract entity, different from all set theoretic objects. Mathematics then concerns what holds true in such abstract structures. Along such lines, all depends on what exactly this amounts to, especially whether one should treat such entities as objects, thus reifying them, making something abstract more, reifying them. Oh shit! Wait, chill. Thus reifying them in a substantive way. Thus reifying them in a substantive way, still to be worked out. Benacerraf himself was reluctant to do so, in line with his overall hesitancy to talk about mathematical objects. A subsequent writer who picked up on Benacerraf's ideas in the early 1980s is Michael Resnick. For him too, modern mathematics involved a structuralist perspective. Following Benacerraf, mathematical objects are viewed as positions in corresponding patterns. And as Resnick adds, this is meant to allow for taking mathematical statements at face value, in the sense of seeing 0, 1, 2, etc., as singular terms referring to such positions. At the same time, doing so is still not supposed to require reifying the underlying structures, which for Resnick would mean specifying precise criteria of identity for them, something he avoids intentionally. He presents himself as Aquinian on this point by adopting Quinn's slogan, "No entity without identity." Instead, Resnick's main focus is on the epistemological side of structuralism, more on which later. Oh, fuck me, dude. Sorry, I just had to see how much I had left. Stuart Shapiro, second philosopher of mathematics, who attempted to build on Benacerraf's paper by focusing on metaphysical questions and by leaving behind Benacerraf's and Resnick's hesitations about structures as objects. Shapiro's goal is to define a more thoroughly realist version of mathematical structuralism. Such realism includes the semantic aspect just mentioned, taking mathematical statements at face value, but Shapiro also clarifies the talk about positions in structures further by distinguishing two perspectives on them. According to the first, the positions at issue are treated as offices, i.e., as slots that can be filled or occupied by various objects. Example, the position 0 in the natural number structure is occupied by 0 in the series of finite von Neumann ordinals. According to the second perspective, the positions are treated as objects themselves, and so are the abstract structures overall. Positions are treated as objects themselves, and so are the abstract structures overall. For Shapiro, the structure at issue thus have a dual nature. They are universals in the sense that the natural number structure, say, can be instantiated by various relational systems, the system of finite von Neumann ordinals, the system of Zermelo numbers, etc. But they're also particulars, to be named by singular terms and treated as objects. To defend the latter further, Shapiro develops a general structure theory, i.e., an axiomatic theory that specifies which structures exist and how to identify them. While clearly modeled on set theory, this theory is justified independently, more on how below. As such, it is meant to underwrite anti-rem structuralism, a terminology that refers to medieval discussions of universals. The crucial point is that the structures specified in the theory are meant to be ontologically independent of, indeed prior to, any instantiations of them. In other words, the structures do not just exist in their instantiations, but separate to and before them. Instantiations? Like instantiated. Oh, I see. While Resnick and Shapiro's structuralist positions are sometimes identified with each other, this is misleading given the difference already mentioned. Nevertheless, there is some overlap. Both recognize mathematical structures as patterns with positions in them, whether these patterns are treated as full-fledged objects or not. Also for both, the notion of isomorphism is crucial, or perhaps some related, more general notion of equivalence, see Resnick and Shapiro. That is to say, for Resnick and Shapiro, a structure/pattern can be instantiated by any of a relevant class of isomorphic relational systems. This corresponds to the fact that the axiomatic systems at issue, those for the natural numbers, the real numbers, set theory, etc., are categorical, or quasi-categorical in the case of set theory. Not every mathematical theory has that feature. Example, the axiom systems for group theory or ring theory allow for non-isomorphic models. According to both Resnick and Shapiro, such algebraic theories are to be treated in a different, more derivative way. Derivatives. Derivatives. So devotions, they're derivatives. Okay. A derivative is called. Jesus fucking Christ. Sorry, I started fucking reading about fucking gradients and partial derivatives. Jesus fucking Christ. Okay, I can't look at that right now. This is too much math. Where did I even stop off at? Derivative. Their structuralist suggestions are meant to apply primarily to no. It's because I read the word derivative. Where did I read the word derivative? More derivative way. More. Their structuralist suggestions are meant to apply primarily to non-algebraic theories. Paradigmatically, like a paradigm, but paradigmatically. Paradigmatically? Yeah, whatever. Arithmetic analysis. There's another structuralist position first introduced in the 1980s that is quite different and explicitly anti-realist, namely promoted by Jeffrey Hellman. While for Resnick and Shapiro, the inspiration was Ben Asaraf's 1965 article, the starting point for Hellman is Putnam's 1967 article. In fact, Hellman's modal structuralism is meant to be a systematic development of Putnam's if-then-ism. The modal aspect, only hinted at by Putnam, is now spelled out in detail, also including the case of set theory, building on work by Zermelo, For Hellman, an arithmetic sentence such as 2 plus 3 equals 5 is to be analyzed as follows. Wait, what? Isn't this necessarily for all relational systems M? If M is a model of the Dedekind-Peano axioms, then 2M plus 3M equals 5M. And to address the non-vacuity problem, Hellman adds the following assumption. Possibly, there exists an M such that M is a model of a Dedekind-Peano axioms. We'll come back to its justification below, which is surprisingly close to Shapiro's in his structure theory. Similarly for the real numbers and for set theory. As Hellman makes clear, his goal is to develop a structuralism without structures. In it, the existence of abstract structures postulated by Shapiro is replaced by the modal aspects of his position, i.e., the assumptions about necessity and possibility just mentioned. In fact, Hellman's position is meant to be a form of nominalism. By eliminating the appeal to any kind of abstract entities, not only abstract structures but also sets, on the other hand, is not meant to rely on possibilia, i.e., possible objects existing in some shadowy sense. This leads Hellman to take the modalities at issue to be basic, i.e., the relevant possibilities and necessities are not reducible to anything further. Possibilia. I like that term. Why can't I? Okay. There. This leads the rest. According to Hellman, such possibilities and necessities are they're specified directly in terms of laws of modal logic. According to Hellman, such possibilities and necessities are an irreducible feature of mathematics, as his approach is meant to make explicit. Fuck. Okay, I can get through 1-3. I can get through 1-3. 1-3. That's easy peasy work. From the late 1980s on, Shapiro's and Hellman's positions have often been treated as the two main structuralist options. This is reflected in Hellman and Shapiro 2019, among others. As they are quite different from each other, this already indicates that it is wrong to see structuralism in the philosophy of mathematics as a unique position or a unified perspective. Even though Shapiro's and Hellman's positions share some structuralist features. From the early 1990s on, other variants of structuralism have started to play a role as well. As a result, discussions of structuralism, the philosophy of mathematics, became richer and more complex, although it was still mostly restricted to metaphysical issues as opposed to adding methodological ones. To clarify the situation, Charles Parsons made several crucial contributions. In particular, he suggested an initial taxonomy based on the distinction between two main kinds of structuralist positions. Namely, there are eliminative forms of structuralism, like Hellman's, and there are non-eliminative forms, like Shapiro's. The elimination issues concerns the postulation or avoidance thereof of structures as separate abstract objects. Jeez, sorry. The elimination at issues concerns. Okay, wait, I read that. Or put in Hellman's slightly later terminology, there is structuralism without structures on the one hand, and structuralism with structures on the other hand. Besides Shapiro and Resnick with the qualifications above, Parsons himself became another proponent of the non-eliminative form, and on the other side, Charles Chehera became another proponent of the eliminative form of structuralism. Nevertheless, it remains widespread in the literature, even today, with exceptions, to identify non-eliminative structuralism with Shapiro's position and eliminative structuralism with Hellman's. Moreover, many discussions of structuralism then focus on Shapiro's anti-rem side, explicitly classified by him as a realist position. Given the latter focus, some critics go on to dismiss philosophical structuralism as a misguided form of metaphysics, one that is seen as relevant for mathematical practice. But such a general dismissal is too quick and inadequate in the end, as we want to emphasize. Even if one just considers non-eliminative forms of structuralism, Shapiro's position isn't the only one. As a further consideration of Parsons' positions already makes clear. Unlike Shapiro, Parsons does not offer a novel metaphysically motivated structure theory. According to him, we can and should instead remain closer to mathematical practice as it developed from the late 19th century on. In fact, for him, structuralist views should be seen as growing out of that practice rather than being imposed on it from outside by philosophers. This means, among other things, seeing abstract structures as introduced directly by categorical axiom systems, a practice Parsons spells out and justifies further in a metalinguistic way. It also means for him that we should refrain from cross-structural identifications, such as identifying the natural number 1 and the real number 1, an identification that can be found in Shapiro's early works, although he later disavowed it. Such putative identities are to be left indeterminate, as Parsons assumes is done in mathematical practice. As this makes evident, Parsons' structuralist position, like Resnick's, is less realist than Shapiro's. In fact, Parsons is explicit that adopting a structuralist view of mathematical objects should be seen as a separable form and orthogonal to the realism/nominalism dichotomy. Consequently, for him, one can be a non-eliminative structuralist without being a realist in any strong sense. His own position is meant to be a case in point. Then again, Parsons' structuralism still takes mathematical statements at face value, so that it remains realist in this minimal semantic sense. In that respect, too, Parsons takes himself to follow mathematical practice. Example, with respect to talking about the natural numbers in arithmetic. Thank you for reading with me. I love you, and I can't wait to read even more. I love you. Have a great day.